Hello and welcome back. We're going to talk about centripetal force and acceleration. Now, I've mentioned this in a previous little video that there needs to be a force that causes the necessary centripetal acceleration for something, you in a car or the car itself or a ball in a string or a planet going around the sun, all of those kind of things. Well, you need a centripetal acceleration towards the center. But as you might think, as you think over those examples, there's lots of different forces that could potentially be causing that centripetal acceleration, right? Because we know already that the net force acting on an object is equal to its mass times its acceleration, right? So if we have an acceleration that is towards the center of the circle, then we need, right? So this is towards the center. And so we need a net force that is also towards the center, okay? And we gave the acceleration here a special name, right? We called this the centripetal acceleration. And as you might suspect, we give the net force that causes that centripetal acceleration the name centripetal force. Now note here that the centripetal force is just a special name for the net force that is required to keep an object going along a circular arc. So just as we don't put, net forces in free body diagrams, we don't put centripetal forces in free body diagrams. And more important than that is that centripetal force can be caused by any number of single forces. And it can also be caused by combinations of forces, okay? Any force that has a component either towards the center of the circle, okay, or away from the center of the circle, so radially inward or outward, is going to contribute to the sum of forces that add up to give you this centripetal force that results in a centripetal acceleration, okay? So the form of that force is just this, right? It's still F equals ma, so there's our net force, our centripetal force. There's ma, right? Centripetal acceleration in this case because we're going around a circle. And here I've just replaced centripetal acceleration with its magnitude, v squared over r. And if we wanted to, we could put some indicator here as to the direction of this, maybe like a little R hat to represent the fact that it's in the direction of the center of the circle, okay? But I'm not too particular on that, as long as you remember that it is always towards the center of the circle. Please, 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 all right? So centripetal force. This is different than centrifugal force. There's some, if you're in my class, there's some resources on our class webpage to talk about centrifugal forces. Let me just say that centrifugal forces are real, quote unquote, and they have important effects, and they are related to the fact that something is rotating or going around in a circle, but it is not what I'm talking about here, okay? Centripetal force is not me mispronouncing centrifugal, so please don't take it as that. And check out those resources about centrifugal forces. We generally won't be talking about them too much here. Essentially, what you can think about, though, is the reason you feel it is because your mass has inertia. It wants to go in a straight line, okay? And it can't if you're going along a circle, right? So if you're in a car and you're going around a curve, you feel like you're being flung to the outside of the car, but that's just because the car is following this path and your body wants to follow this path. And so until you lean up against the door or the seat belt or the friction with the seat and your body conspire, you will try to move in the direction of your velocity at that moment until you are acted upon by an outside force that brings you along the curved path. Okay, so centripetal force is defined in this way, and I wanted to point out a couple of things about it. Okay, one, we've already discussed this, and you see that on the diagram, that is in the same direction as centripetal acceleration. And it's a net force. Let's say it one more time, and I'll put it in text. It is a net force. It is caused by normal forces or forces of tension or forces of gravity, depending on the situation that you're considering. What object is moving in a circle? And we'll look at one of those situations in a sample calculation right now, okay? So let's consider a penny sitting on a turntable. And we have one of those turntables that don't just have the settings. We can just turn a knob continuously and make it go faster and faster and faster. And what we would like to know is the maximum speed of the penny that will allow the penny to stay put. In other words, not fly off the edge of the turntable here. Okay? So, a couple of things. One, the radius here would not be of the turntable. It would be to wherever the penny is sitting, right? The circle that you're considering in centripetal force, centripetal acceleration problems, is the radius of the circle that whatever object you're considering, the penny here, is tracing out. So that's the little dotted gray line here that I put in, okay? And I've indicated the direction of the centripetal acceleration, just as a little reminder that it's in towards the center of the circle. And we're given two quantities and two quantities only in this problem, which is the radius of the circle that the penny is tracing out and the coefficient of static friction between the penny and the surface of the turntable. Now, you might sort of look at the expression for centripetal force and say, okay, well, don't I need to know the mass? Okay, don't I need to know that? You could say, oh, well, it cancels out here, right? It's on both sides, but wait. That would just reduce to centripetal acceleration is equal to v squared over r, right? We could do that, but it's not very helpful to us right here. Because we're looking for this, okay, and we don't know that. So that approach is not going to be fruitful, okay? But we are moving around in a circle, so we're pretty sure we're starting with this principle. Let me just write it in this form. And the question you always want to be asking yourself when you're doing a circular motion problem is, what forces are causing the centripetal force? So if we look at our penny in the diagram here, and let me grab a different color, because otherwise it might be a little tricky to do. Actually, maybe red's not the best. Green. Well, there are a couple forces here. One would be if we sort of drew the penny on its side. Okay, so the center of the circle's over here. There would be normal force from the turntable upward on it. There'd be force of gravity downward on it. It's not accelerating vertically, so I should try to draw those to be about the same length, and I've sort of succeeded there. But then, in terms of the thing that would actually cause it to stay on that circle, so in other words, a force that's acting towards the center of the circle to give us that necessary centripetal acceleration, well, the only real option here is the force of static friction. Now, why must it be that? Well, remember that the penny, according to Newton's first law, wants, quote unquote, right, to go in the direction of its velocity unless it's acted upon by a net external force. And indeed, it is being acted upon by a net external force. And the only possible one, because we've exhausted our force at a distance, and it's only in contact with the turntable, so things like drag and whatnot are not going to be significant and wouldn't be towards the center of the circle anyway. Force of static friction, by kind of process of elimination, is the only force left, right? And if it wasn't there, well, then the penny would just go off in the direction of its velocity, like a car hitting a patch of ice as it goes around the curve. It loses friction between the tires and the road, and it just goes in whatever direction its velocity was at that moment when it lost traction. Okay, so we've answered the question, what force or forces are causing the centripetal force. So we can set the centripetal force equal to the force of static friction. And we know that the force of static friction is equal to mu s F sub n. Okay? And you might say, Dr. Fairbanks, we learned that the force of static friction is not equal to, it is less than or equal to the coefficient of static friction times the normal force. And you are correct. However, we are looking for the maximum speed here. So if we're going faster and faster and faster and faster, the force of static friction that needed to keep it on the circle when it's going really slowly, so the rotating table is just going around like nice and leisurely, would be small, right? And it would get bigger and bigger and bigger and bigger and bigger and bigger until it hit its maximum value. And if you went even a little bit faster than that, well, then it would be flung off of the turntable, right? For a force of kinetic or static friction would turn into force of kinetic friction. And that's something that you don't want in this problem, right? You want this penny to stay put. So we are free to put in the maximum value of the force of static friction. And we're still kind of stuck. We're looking for this V. We don't know M. We know R. We know mu. So we're doing well on those two things. But we can make one more substitution, right? There are only two vertical forces acting on our penny. So they must be equal and opposite because there's no acceleration in the vertical direction, right? The penny's not burrowing into the turntable and it's not levitating up off of it. So we can replace F sub n with the magnitude of the force of gravity, and that gets an M over on this side and an M on this side. And so we don't even need to know the mass of the penny. Away it goes. And we multiply both sides by R, and then take the square root of both sides. And we're left with an expression that can give us our maximum velocity. We know we're at the maximum velocity because, again, we use the maximum maximum value of the static friction force. Okay. Now, if you plug that in, so we got 0.45 times 9.8 meters per second squared times 0.15 meters, converting from centimeters. If you plug all that in correctly, pardon me, I think you get just over 0.8 meters per second for our V max. Okay. So this kind of procedure where you're recognizing you're moving in a circle, looking at the forces acting on the thing, figuring out which one of those forces, or which forces potentially, can possibly be contributing to the centripetal force, and then making substitutions until you can find the appropriate thing, perhaps breaking out a definition of force of friction or something like that, is generally the procedure that you will be following with circular motion problems, though every one will look a little different. So I hope this was useful, and I will see you for the next one.